Hot Chemistry 12.2. This is the third video for week 4. In this video, we're going to take a look at pH and pOH. So looking at the pH scale and the relationship between pH and pOH and concentrations H positive and OH negative. You'll find it on page 596. It's still in section 19.2 in your textbook. So we're going to take a look at a few new formulas during this video. And I know we don't often talk about formulas in chemistry, but I have posted a formula sheet in the week 4 references or resources. And I think it's well worth copying out or printing off so that you have these formulas handy. The formulas aren't hard to use, it's just knowing how to use your calculator to do these formulas. So the better part of this video will be explaining how to put this information into your calculator. So a scientific calculator is important. So if you need to pause and go hunt down a scientific calculator, please do that, okay? Because I want you to be able to know how to put this information into your calculator. So we're going to talk about the pH scale. You may have talked about it before. It is a scale that's related to acidic and basic solutions. A fellow named Sorensen actually was his name. I don't know if his mom didn't like him, but Sorensen was working with concentrations of H positive and OH negative. And in the last video, we talked about the fact that they're very, very tiny. So when water ionizes into its ions, or self-ionizes, or auto-ionizes into its ions H positive and OH negative, the equilibrium is very, very, very reactant favored. And so we talked about 1 billion water molecules, only two will break into their ions. And so when we look at the concentration of these ions produced, we're talking about tiny, tiny numbers. And so Sorensen wanted to a more workable measurement when we talked about concentrations of H positive and OH negative, because when you look at those concentrations, they're very, very helpful to talk about how acidic or basic solutions are. So if we take a quick look at this this diagram down here from your textbook, it does a pretty good job comparing concentrations of H positive and OH negative and the pH scale. So you'll see on this column here the pH scale 7. 7, a lot of people say 7 is neutral. Not necessarily. We already talked about the fact that a neutral solution is all about having equal concentrations. At 25 degrees Celsius, it happens to be at a pH of 7. But if you fluctuate that temperature, you might have a neutral solution that's a little lower than 7 or a little higher than 7. So the pH doesn't dictate neutrality. It's the equal concentrations of H positive and OH negative. That's what dictates a neutral solution. And we talked about in the previous video, if you have higher concentrations of H positives and lower concentrations of OH negative, you have acidic solutions. So how the pH scale works is it's a logarithm. I know in math class, Mrs. Baker talks about logarithms, and she actually uses pH scale as an example of how logarithms work. So if we start here at our neutral solution and we have -7, exponent of -7 and exponent of -7, because those concentrations are equal, we know it's neutral. But as the concentrations of H positives go up, now be careful, because they're negative exponents, the exponents are actually decreasing, right? An exponent of -1 is a lot bigger than an exponent of -5. So be careful with this. It looks like our numbers are going down, but in fact, the concentration of hydrogen ion is going up. So we have high amounts of H positive. And we know if we're on that teeter-totter, the relationship between H positives and OH negatives, as the H positives go up, because Kw is constant, the OH concentrations go down. So see, we're starting at -7 here, but as we move up the chart, we're dropping in concentration, so our exponents are getting bigger. So when we look at our pH, it's comparing it to the H positive concentration. So as our H positive concentration increases, the exponent is decreasing. And when you take a negative logarithm, if it's a base 10, you're in fact actually taking the exponent and turning it positive. So if you take the negative logarithm of 1 times 10 to the negative 6, you get a value of 6. If you take the negative logarithm of 1 times 10 to the negative 3 rather, you get a pH of 3. So even though it looks like the numbers are dropping, well, it doesn't look like it, the numbers are dropping. So when you look at a pH scale, as the numbers go down, you actually are getting more and more H's, which means you're getting more and more acidic. So as the numbers go down, you're approaching a very acidic solution. The opposite is true in the other direction. So here we're neutral, and as these exponents climb, we're getting smaller and smaller amounts of H positive. If that's happening, we know that we're getting larger and larger amounts of OH negative. And so the pH is referring to the H positive concentration. So here, as the H positive concentration drops, the exponent gets larger. So if you take the negative logarithm of 1 times 10 to the negative 11, you get 11. The negative logarithm of 1 times 10 to the negative 12, you get 12. So Sorensen was just trying to come up with a more usable scale to measure how many H positive, or what the concentration of was what the concentration is of H positive. And this is just a more manageable scale. Okay, so I hope that's clear. You can see some of the examples of basic solutions, acidic solutions, and here we have our, oh, I don't know what happened there. We have our pure water, which in this case is neutral because these two concentrations are equal. If you look at the exponents, or rather the formulas, this is how we can move from H positive to pH, okay? It's also true when you look at OH. So you can have a pOH scale or you can have a pH scale. The pOH is when we're comparing to the hydroxide concentration, and it's negative log times the concentration. You can rearrange this formula. So if you have one piece of the puzzle, you can always find the second. So and when we rearrange this, we would divide both sides by negative log. So H positive is pH minus log or minus pH over log. It doesn't matter where you park your negative there when you look at that. Okay. All right. So one more thing I wanted to talk about, and that is going to be sig figs. So I think we'll try these with our calculator first, and then we'll talk a little bit. The sig figs are a little wonky when it comes to the pH scale. I guess one more thing I would mention. The maximum on a pH scale is 14. The minimum technically is 0, so it's a scale from 1 to 14. 7 being neutral at 25 degrees Celsius. So if your temperature fluctuates, 7 might not necessarily mean neutral. And as you drop to 0, you're getting more acidic. Why? Because you're having more amounts of H positive. And when you increase to 14, you're getting more basic. Why? Because you have larger amounts of OH negative. Okay. What's true though is because of the scale, we also can look at this relationship. pH plus pOH is always going to equal 14. Just like Kw, remember OH negative times H positive always equals 1 times 10 to the negative 14. Kind of along the same idea. pH plus pOH is always equal to 14. Again, at SATP. So at 25 degrees Celsius, these formulas are true. Okay, so I'm not there with you, so I'm going to try and explain how to put these things into your calculator. You want to practice so that you're getting the same number I'm getting, and that way you kind of know you're putting it in the correct way. So we take this example here. It says communicate hydrogen ion concentration of 4.7 times 10 to the negative 11. Okay, so it's a pretty small concentration, and we want to turn that into a pH scale. Now some people will say, oh, it's 11. You've got to be careful. That's only when the front number here is 1. So yes, 1 times 10 to the negative 11 You just change the exponent sign, so you'd have a pH of 11. But this has not a 1 in front. It has 4.7, so we've got to do a little more work to change this into a pH. So here's our formula. pH equals negative log of the concentration of H positive. So the concentration of H positive is 4.7 times 10 to the negative 11. Now, some calculators, you start in the front and you just keep trucking. So you would hit negative positive button, your log button, and then your concentration. That should give you 10.33. My calculator from the dollar store works in the opposite direction. So I put my concentration first, then I put my log, I hit my log button, and then I hit my positive negative button. So you might be moving in this direction, so put your concentration in, then hit your log button, and then your negative. Or you might be going in the forward direction, so you hit your negative positive button, your log button, and then your concentration. So try a couple different ways to make sure you're putting this in okay. So 4.7 exponent, right? And I'm putting in 11 negative, so I want to put in a negative exponent of 11. Sometimes you have to put negative positive 11. I can put 11 negative positive. And then I hit my log button, and then I hit my negative positive button again. So I'm getting 10.327. So I'm rounding that up to 33, and I'm going to tell you why in a second. Okay, so try that a couple different ways. As long as you're okay with your calculator, that's what's important. So with my calculator, I work backwards. I put the concentration in, 4.7 exponent, 11 negative. So I put in my concentration, I hit my log button, and then I hit my negative positive. So I get a positive 10.33. For others, you'll put in your negative positive button, you'll hit your log button, and then you'll put 4.7 times 10 to the negative 11. Regardless of how you put it in, everybody needs to be getting 10.33. If you're not getting 10.33, we're doing something incorrectly. So where the sig figs come into play, and I'll reiterate this in a minute, but see how we're looking at this concentration. And if I was going to count the sig figs, we only count the number in front of the times 10 to 11. So this has 2 sig figs. So a lot of people are like, this has 2 sig figs. Why are you putting so many down here? That's because sig figs are kind of unique when you talk about pH and pOH. And how it works is if you have 2 significant figures in your hydrogen ion concentration, when you do pH, we don't count the numbers in front of the decimal. We only count the numbers after the decimal when we do sig figs. So this, we count all of them, everything in front of the times 10 to the 11. But when we look at the pH, we're only counting the 33, 3.3. Those are the 2 sig figs. We could have about 20. Well, we won't. But we could have anything between 1 and 14 in front. It's the numbers after the decimal that we count. 2 sig figs here, 2 sig figs here. Let's try another example. Here we're doing the opposite direction. So, excuse me, we're starting with a pH, right? We're starting with a pH of 10.33. We might as well keep it simple. And we're looking for our hydrogen ion concentration. So we're working backwards, okay? So you can take your original formula and you rearrange it. So H plus is your pH divided by your negative log. Now, we don't literally divide by negative log when we use logarithms. We actually, instead of, whenever you see that you want to divide by log, on your calculator, you're going to use the inverse log or the shift log option. So if I was going to put this into my calculator, I'm going to take my pH, which is 10.33, and I'm going to divide by inverse log. Now, some people like to park that negative up here with the pH, and that's okay too. So on my calculator, I would put in negative 10.33 second function log, and I should be getting this value right here. Okay, try it on your calculator. So 10.33, and I'm going to put my negative in front of that, and I just hit my second function log. I'm getting 4.67, so I rounded up to 4.7. Reason why, when the here, right, it's a pH, so I only count the digits after. So there's 2 sig figs here, So when I come up with my concentration, I need 2 sig figs here. Okay? So that's how I put it into my calculator. You might want to fess around a little bit and make sure you know how it works for you. You can also, if you want to think about it this way, right? If you're looking for your, it happens to be OH here, but if you're looking for your concentration, you can also take 10 to an exponent of negative pOH. So if we were doing this for our question we just did, we can also think about it as your H plus the concentration equals your 10 to 10.33. You can think about it that negative. You can also think about it that way if you want to. Okay, whichever works for you, but you want to make sure you practice enough so that you can convert pH to H positive, or H positive to pH, or pH to pOH, or pOH to H. You want to be able to go back and forth between these variables. So I wanted to do one more example with you before I send you on your way. Here's an explanation. I pulled it right out of the textbook. Here's an explanation on that wonky significant figure info, so you can read that again. But I'm going to solve this question, and I'm going to solve it in 2 different ways, especially with pH and pOH. There's always more than one way or one method to solve it. So I wanted to do it 2 different ways so you could see that our answers come out to be very, very similar. They're not exact because of the rounding off that we did, but they're very, very similar. And I'm also going to point out the scientific or the significant figures. So let's say we know our concentration for OH is 4.26 times 10 to the 4 molars. And we're wondering what our pH is. See, they don't match up, so it's not as easy as the last slide, but not a big deal. In order for us to find pH, we can do it in 2 different ways. One way we can do it is we can use this information, and instead of finding pH right away, let's find pOH. We can directly link those 2 together. So if I'm looking for my pOH, it's negative log OH negative. So negative log, and I bring this concentration down. Okay? When I plug that into my calculator, you might be putting in negative log and the concentration. On my calculator, I put the concentration in, then I hit the log button, and then I hit my negative positive button. Regardless of which way you're putting into your calculator, you should be getting 3.371. Why did I put all of these digits here? Well, let's review. Up here, it's a concentration, so I count all the digits in front of the times 10. There's 3 of them. When I do a pH or pOH, doesn't matter, I only count the digits after the decimal. So there's my 3 sig figs. Okay? Now, I'm not at pH, but I'm at pOH. And if you recall, there's a nice relationship between pH and pOH. They add together to give me 14.000, as many zeros as you need. And so by knowing that one of them is 3.371, I can take 14 and subtract 3.3. Oh, that's why it didn't work out. Oh, even better. 3.371. And when I do that, I get an answer of 10.629. I guess it didn't make much difference. So 10.629. Well, actually, it makes a big difference because both methods are going to work out exactly the same way now. Yay. So that's one way you can do it. You knew your OH, so you went directly to pOH, and then remembering pH and pOH equals 14, by subtracting you found your pH. That's one way you can do it. What's nice about pH and pOH, there's always more than one way. So same question, 4.26 times 10 to the negative 4, we're looking for pH. Okay, we want pH, we know we can't directly use OH, so let's use our OH to find the H. This is what we were doing in the last video. So using our KW, rearranging the formula, we can come up using our KW and using our concentration for OH, we find the concentration for H positive. Okay? Once we have the concentration for H positive, we plug it into our pH formula, negative log concentration. And we get an answer of 10.629. So we get the exact same answer. And check out the sig figs. This guy has 3. So when we found H positive, it had 3. And when we did the pH, we have 3 digits after the decimal. So a little different. It really just takes some practice with these things, making sure you're okay with your calculator and putting these information into your calculator. So here's the equations I was talking about, minus this. We'll talk about this in the next unit. But these are the equations you can find on that formula sheet that I included for you. And one last thing. If you think about, let's just revisit this autoionization again, okay? And so I'm just going to bring that over here. When we talk about autoionization or self-ionization with water, we're looking at these 2 water molecules. They're colliding and brushing against each other. When that happens, one of the hydrogens get dislodged. And so this water picks up an extra hydrogen and this guy loses one. This becomes H positive or H3O positive, hydronium ion, and this becomes OH negative. We know that the relationship between these things dictates if we have a neutral solution, a basic solution, or an acidic solution. When these guys are equal in amounts, we're neutral. When we have more H positives, this guy drops, so we're acidic. If we have more OH negatives, this guy drops, so we're basic. You can use Kw, and Kw is that product ion product constant. That's what Kw is. So taking these 2 guys, multiplying it together, always going to be 1 times 10 to the 14. So if they're equal in pure water, we're assuming it's neutral. So in pure water, these guys are equal. So if we use x to represent each of them, we can take the square root of our Kw and get our value for x, which would be the value for both of our solutions. If we plug that into our formula, we're going to find that we have a pH of 7. But we've got to be careful. Up until this point, you've probably been told that anything that has a pH of 7 is neutral. And that's true, but we can also have neutral solutions that are a little lower or a little higher than pH. Because technically, guys, the temperature plays a part here. So when it's 25 degrees Celsius, that's when you have that pH of 7, and that's when it's neutral. That's when you're guaranteed that you have equal amounts of H3O positive and OH negative. But what happens when we change that temperature? So this self-ionization is an endothermic reaction. And if you remember from our first unit, if it's an endothermic reaction, we put the energy on the reactant side. Okay? If it had been exothermic, we would have put the energy over here, but we put it on the reactant side. So what's that going to do for us? It says, imagine if the temperature goes up. Let's do a little Le Chatelier's principle. What happens if we don't have 25? Let's say we have 30 degrees Celsius. What happens when the temperature goes up? We know if it's an exothermic change, if we increase the temp, if that's our stress, an increase in temperature, which way is this going to shift, right? I hope you're saying it's going to shift to the right. And yes, it does shift to the right. And when it shifts to the right, it uses the stuff up and it makes more ions. So if the temp goes up, we have an increase in these guys, right? If the temp goes down, we'd have a decrease in those guys. So the temperature plays a really important role in the concentrations of your H3O positive and your OH negative. What does this mean for the pH and the pOH? Now be careful. If the exponents are going up, what's happening to the pH and the pOH? Right? So if we were, let's say, at 10 to the negative 7, and now it's 10 to the negative 6, we've got more H positive ions. What's that do to our pH? And our pOH, it decreases it. Okay? They're kind of opposite. So as the concentration goes up of H3O positive, the pH goes down. So does this mean it's not neutral anymore? Right? So here's an example. If H positive, H3O positive is now 1 times 10 to the 6, then what would the pH be? You can plug it into your calculator, but look, we have that 1 in front. So we literally can take our exponent and change the sign. So the pH is going to be 6. Okay? But it's still considered neutral. Why do you think it's neutral? Well, if you're saying it's neutral because if you look at the equation, the mole-to-mole ratio between H3O positive and OH is 1 to 1. So if the pH goes to 6, guess what? These guys have equal amounts here because it's still a neutral solution. So the pH is going to be the same for both of them. Okay. If the pH of water at 10 degrees is 7.25, then what is the pOH of water at 10 degrees? And this is what's key. If water is pure, regardless of what the pH is, the pOH is always going to be the same. And it's always going to be the same because the true definition of neutral is when your H positive ions equals the concentration of your OH negative ions. So I went a little longer, of course, as I anticipated, but hopefully that gives you a pretty good overview of the pH scale and how we can use our calculators and formulas to convert between pH, pOH, H positive concentration, and OH negative concentration. Thanks for your attention. Bye-bye.